This is the topic 4.4, calculating average atomic mass. So right now we've talked about mass number, which is the protons and neutrons in the atom. In this particular video, we are going to show how average atomic mass on the periodic table is calculated. Because again, that mass displayed on the periodic table is not necessarily going to reflect the mass number of a specific atom because we have isotopes. So if you don't have your periodic table and a calculator, go ahead and take a moment to pause this video and go get those two resources, please. So like I just mentioned, when it comes to the mass of the atom, the two subatomic particles truly responsible for it is the protons and neutrons. Electrons do not do much in terms of the mass of the atom. So this particular periodic table is set up a little bit different, but if you look at yours, this is the same number displayed at the bottom of the box for the element chlorine. And so why do we have a decimal? Because everything at this point with mass number has been a whole number because we count protons and neutrons using 1 AMU. And so you can't have a third or a half or 3/4 of a proton or a neutron. You can only have them in whole amounts. And so this is reflecting the fact that chlorine has different isotopes, therefore different masses. And so we're going to show how that number comes about. So average atomic mass is what's called a weighted average. So you may have classes now that work that way, and here's kind of an example with that you have these categories that are worth different quantities. So in this particular person's class, quizzes are worth 20%, exams are 35%, and this term paper they have is 45%. You may not have classes do that now, but especially in college, they tend to weight categories where it accounts for this term paper carries more weight in factoring your grade than your quizzes do. And so what we do for that is here, lithium, for example, has 3 isotopes, lithium 6, 7, and 8, meaning they have a different number of neutrons to give us this different mass number. And so the next thing that we need to account for is that these are not equally abundant in the world and that it's not evenly split at basically 33% for each. Different isotopes have different abundance or how much they occur naturally. And so we have to account for basically the percentage of the population for each isotope. So this is the steps of what you do to calculate average atomic mass. I will walk you through this when we get to the problems. So how do we even know that there's different isotopes out there, and how can we figure out what their abundance is? What we use is a mass spectrometer. So here they inject chlorine gas into this particular, if you're studying chlorine, into this chamber here. They have 2 different colors here, this darker green and light green, to represent the 2 different isotopes. And you can see that the majority of it is this dark green, which is representing the isotope chlorine-35. The light green, which is less abundant, chlorine-37. So what it does is it passes through this chamber of electrons. And when it goes through this beam of electrons, it basically ionizes it, meaning it gives it a charge. And that's very important to take it from a neutral atom to a charged atom, because then we can turn it into this beam of ions. And again, ion with a charge, these are cations. So when we put them in a magnetic field, we have charge, and that's important because then we can start separating them. So because we put them through a magnetic charge and we have our magnetic field and these particles have a charge, we can then separate them. We get a beam that goes this direction for the chlorine 37 and this beam here for chlorine 37, and we have this detection plate that can then determine the difference in mass based on how they deflect. And so then we can start looking at basically how many times this one counts the atoms versus this one here. And so we can see that the chlorine-35 has a higher percentage than chlorine-37. So this is what it looks like from the outside. So if you guys go on to take chemistry in a college setting, you may get to use a mass spectrometer. And so I've got to use them back in my college days as well. So what this looks like, so this isn't official, but this is kind of mimicking if you were using that spectrometer, what would the information look like and what do you do with it? So we're going to work through 3 examples with element A, B, and C. And so this is spectrograph for element A. Across the top, we have their mass. Across the bottom, we have their percentages. So this one really doesn't have much of a calculation because 100% of it is made up of only one type of isotope, or it has only one mass. And so what we can do is, this is automatically telling us our answer here, that because 100% of the atoms have this mass, the average atomic mass is going to be 27 AMU, or atomic mass units. So the next thing that we can do is then use our periodic table to identify what is this element. So what you're going to do is, if you find the one that I gave you, if you look across those bottom numbers, and for the most part they go in increasing order, there we'll talk about some patterns that don't demonstrate that later on, but you're looking for what element is closest to 27. Well, when you hunt it down, you'll find out that it's closest to the element aluminum. Okay. As we move on to example B, we now have 3 different isotopes with their coordinating mass. So now we have to calculate a weighted average because we have more than one isotope, or we have more than 100% abundance of a type. And so this is how we're going to calculate that weighted average. So the first thing that I'm going to do is write out my 3 percentages. I have 11.2%, I have 10.1%, and let's see, that's 78.7%. So the first thing that you do when you calculate a weighted average is you must convert your decimal, or your percentage, to a decimal. And to change a percentage to a decimal is to use division and to divide by 100. Or essentially, you always move it 2 decimal places to the left, like with scientific notation. So the first thing I'm going to write inside a set of parentheses is 0.112, 0.101, and 0.787. Again, I got that by moving the decimal 2 places to the left on all 3 percentages. We then weight that into each mass. So we multiply that by the corresponding mass. So 11.2% went with a mass of 26 AMU. The 10.1 went with 25. And lastly, the 78 went with 24. So again, what this is doing is factoring in that the majority of the mass is coming from this isotope here, and these other 2 are not contributing much in terms of the population. So when you think about it, our average atomic mass is going to be relatively close to 24, because again, this is where the majority lies. The nice thing about these is you can type them in all at once. I would do parenthesis, type in your 0.112 times 26, close that parenthesis, add it, put in your next set of parentheses, add it, and add your third. So again, you can do this all in one step. You don't have to simplify it out step by step, quite like we did with conversions, for example. So when I did that, we're going to go with sig figs based off the percent here, just to make it a little bit easier, especially for identifying it. We get 24.3, and again, our unit is atomic mass units, or AMU. And so then again, we're going to identify it. So when you use those average atomic mass, again found at the bottom of each element box on your periodic table, you're going to find that it is magnesium, or Mg. So now we have one last problem. We have example C here with 4 percentages. So we have 2.18%. So just like last time, the first thing I'm going to do is go ahead and write these out. And then just like last time, the very first step is we need to convert these into decimal form. Again, the one thing I see students do often is they just move it just however many places to end up with it one spot to the left of the number. Again, you're moving it 2 times, no matter what your starting percentage is. So when you do that, this one becomes 0.0218. So again, just make sure that you're being careful and moving your decimal 2 places each time. So again, we can see the majority is going to be with that 83.9%. And so we're going to go ahead and write those corresponding masses down. So we have 54, and 9% goes with 53. So most of our mass is in that 52 range. So we should expect our average atomic mass to be relatively close to that. So same idea, we can type all 4 of these in at once. Again, parentheses are your friends here, so use parentheses, type in your percent times your atomic mass unit, close that parenthesis, add, and then like I said, just type this in all at once. We will use 3 significant figures because of our percentages here. And so when we go about doing that calculation, we get an answer of 162 AMU. So this one's a little tricky to find. The periodic table does deviate. When you start looking at it, there's a section that's cut out, and we'll talk about why as we make our way into our next couple of units. So this one is found in that bottom segment of the periodic table, and this has a symbol of dy, or dysprosium. This will probably be the only time we will ever use this element. This is not one that is used very frequently with the calculations that we do. So this is how you do average atomic mass. So there's one other way that we can look at average atomic mass, and that's doing what's called relative abundance. So the difference in these problems is that the percentages aren't given to you, and that's what we're solving for. So let me work through this, and I would definitely recommend watching this section maybe once or twice. And again, really make sure that you're taking these notes and writing them down. So antimony has 2 naturally occurring isotopes. The mass of antimony 121 is 120.904 AMU, and the mass of antimony 123 is 122.904. Using the average atomic mass from the periodic table, find the abundance for each isotope. So when it says find the abundance, that means you are determining the percent abundance for each. So we are not calculating the average atomic mass like we did in the previous examples. We are solving for the percentage for each given isotope. So it says right here, use the average atomic mass from the periodic table. So antimony has the symbol SB. And when you track it down on the periodic table, the number again at the bottom is the average atomic mass. So when you find antimony, we find that it is 121.760 AMU is the average atomic mass. So the next thing is important. It says, remember that the sum of the 2 abundances must be 100. So we can use that to our advantage, that we know 1% plus another percent should always come out to 100. The next thing we have to recognize here is that 100% in decimal form is equal to 1. So the idea when I go to set this up is I have my 2 isotopes. So I would have parenthesis, and the first thing I would write in is my percent that I'm solving for, or the percent that I'm given in decimal form. We don't have that. So I'm going to make that X times its average atomic mass. So the first isotope given to me is the 120.904. Adding it to my second isotope. Now this is the part we have to think about. It said both percentages, the sum of them equal 100. So our X is not the same in both instances because they are going to have different percentages that they are abundant. So what we have to do here is we would have 1 minus X, meaning 100% minus whatever percentage this isotope is abundant is the second percent, times its mass of 122.904 AMU. And like in the last problems, we were calculating average atomic mass. So again, we've already been given that from the periodic table, and that is 121.760. So the next thing I'm going to do is actually eliminate my units real quick. So that way it's a little bit easier to see the algebra that we're going to be doing here. So I'm just going to rewrite what I have. So hopefully that makes it look a little less scary. And so again, you just have to work through it using algebraic skills. So think about what you need to do to simplify to solve for x. So let's take care of this first part. To simplify here, we're going to multiply. So it just turns into 120.904x. Inside these parentheses, we're multiplying. So that means we need to distribute. So we're using our distributive property here. So we get for the first part, 122.904. For the second part of the distribution, we get negative 122.904x is still equal to our average atomic mass. So again, as I've gone through my steps, I just eliminated my units going from here to here. And here, all I've done is started simplifying out the algebra. Now what we want to do on this side here is start combining like terms. The only thing we have is this here and here. So we're going to take 120.904 minus 122.904. When you do that, you get negative 2x. And this is still left over, this term here, so plus 122.904. Still equal to our average atomic mass of 121.760. Okay, so again, our goal here is to start eliminating to get x on its own. So we need to move this variable here, or this term. So we're adding currently. So order of operation that's opposite is subtraction. So we'll subtract that from each side. So we get negative 2x is equal to, and this is equal to negative 1.144. Last thing, we just need to divide by a negative 2 to get x on its own. X is now equal to 0.572. Okay, so what does that information tell us? Remember, this is a percentage that is in decimal form. So how do we get it into a percentage? We're going to multiply by 100. So that means that x is equal to 57.2%. This was my x here that went with this isotope of antimony 121 because it had this mass here. So I'm going to write that down here. SB 121 is 57.2% abundant. We had one other isotope because again, this isotope plus this isotope equals 100. So I need to take 1 minus x. So 1 minus 50.572. Or you could take 100 minus 57.2, and that's going to give me my SB 123, and that is going to be 42.8%. And we have worked out those 2% abundances. So we have one more example that we're going to do. And if you're still feeling a little bit lost, I would highly recommend, once you have wrote this out, just rewatch the video again for this segment. So now we're going to talk about europium, EU. It has 2 isotopes with a mass of 151 and 154. And it gives us the average atomic mass in this problem. So in the last problem, it told us to use the periodic table to find it. In here, it gives us the average atomic mass. And then here it's asking what is their abundances, aka we're going to figure out their percentages. For this one, the masses are given to us already in whole numbers instead of the AMU format. And we still have 2 isotopes. So what I'm going to do is I'm solving for percent. So that's my x times its mass. So this first one has a mass of 151. Again, my 2 isotopes combined together give us 100%. So the second one will be whatever the first one is minus 100 or minus 1 times its mass of 154. So again, the second number we got from the periodic table, or this ending number, I really should say, but they gave it to us. Like I did in the last problem, the next step I did is just dropped my units for now, just to make it a little bit less intimidating and give me a little bit less going on. So it's a little bit easier to see the algebra. So I've kept everything the same at this point. And much like the last problem, your next step is to work through it algebraically. And the best thing to do here is just start simplifying. This one just multiplies out to give you 151x plus, this is using distribution to simplify here. So my first term multiplying by the 1 is going to be 154. My second term multiplying by negative x gives me negative 154x. Still equal to that average atomic mass. Our next step, combine like terms. So on the left side, the only like terms that we have are the two with the x, 151x minus 154x. When that combines, we get negative 3x. We still have that plus 154. So let's start working to get x on its own now. So to do that, we need to subtract the 154 from both sides. When we do that, we get negative 3x is equal to negative 2.03. We have one last step. To get x on its own, we must divide by negative 3 to each side. We get x is equal to 0.677. Again, what that's telling me here is this is my percentage in decimal form. So for this first isotope that we're identifying as x is going to be 67.7%. So we are going to say that the europium 151 Okay, now we need to solve for our second isotope using the idea that percentages add up to 100. So once you're here, you can just take 100 minus 67.7, or you can take 1 minus 0.677 and change it to a percentage then. But when we do that, we get 32.3%. So we have two style of problems that we can use with this information. The first side, the first three problems, we're using average atomic mass, calculating a standard average atomic mass, identifying the element. The one thing that's nice about that is you can use your answer and compare it to the periodic table, and that's kind of a way to help check your answers. In these last two examples, this is what you work through to figure out what's the percentage of each. Again, if these last two were confusing, the first thing I would recommend is rewatching the segment. Try working a problem out on the homework once you get there. Send me a picture of it or set up a Google Meet, and I will gladly work with you if these last two gave you trouble. So again, make sure that you show your work, keep track of sig figs, and show your units. Some of you guys really got dinged on your test for doing that, and I've been telling you in the homework, you need to show those steps. So again, show your work.